This is my third lecture on the topic enzymes, and today I will discuss enzyme kinetics. First, we must know what is Gibbs free energy. Gibbs free energy is denoted by delta G, and delta G depends only on the free energy of the products minus the free energy of the reactants. In this graph, the free energy of the ground state of reactant is at a higher level and free energy of the ground state of product is at a lower level. So, the delta G value is negative. And if the delta G is negative for a reaction, it means the reaction is spontaneous and it is exergonic. If the delta G value is 0, it means the reaction is at equilibrium. At equilibrium state, the rate of forward reaction is equal to rate of backward reaction and there is no change in the concentration of reactants and products with time. If the value of delta G is positive, then it means the reaction to proceed needs an input of energy and the reaction will be endergonic. So the value of delta G provides us the information whether the reaction is spontaneous or not, or whether the reaction is at equilibrium. Whereas delta G does not tell us about the rate of reaction. And the other thing we must remember is enzymes do not affect the Gibbs free energy of a reaction. The rate of reaction depends on Gibbs energy of activation, also known as free energy of activation. And activation energy is the minimum amount of energy that is required to activate atoms or molecules so that they can undergo chemical transformation. Any reaction such as conversion of substrate to product or vice versa can be described by a reaction coordinate diagram. Reaction coordinate diagram gives us a picture of the energy changes during the reaction. In the reaction coordinate diagram, the free energy of the system is plotted against the progress of reaction. And starting point for either the forward or the reverse reaction is called the ground state. In this diagram, the free energy of the ground state of P is lower than that of S. So delta G of the reaction is negative and the equilibrium favors the formation of P. The reaction is thermodynamically possible and is spontaneous if the free energy of the ground state of product is lower than that of substrate. But a favorable equilibrium does not mean that S to P conversion is fast. For conversion of S to P, extra energy is needed. And why this energy is needed? This energy is needed for alignment of reacting groups, formation of transient unstable charges, bond rearrangements and other transformations required for the reaction to proceed in either direction. And the extra energy that is needed for the reaction to occur is represented by an energy barrier or a hill. The top of the energy barrier is called transition state. And at the transition state, certain events like bond breakage, bond formation, etc. decide the future course of the reaction. The difference between the energy levels of the ground state and transition state is called activation energy. A higher activation energy or a larger hill represents a slower reaction. And if the activation energy barrier or the hill is smaller, that means the rate of reaction is fast. The reaction rates can be increased by either increasing the temperature or by adding a catalyst or an enzyme. Catalyst or enzyme enhance the reaction rate by lowering the activation energy. Enzymes catalyze reversible reaction. That means any enzyme that catalyzes the reaction S to P also catalyzes the reaction P to S. The role of enzyme is to accelerate the interconversion of S and P. The enzyme is not used in the process and enzymes do not affect the equilibrium. However, The reaction reaches equilibrium much faster when the appropriate enzyme is present. Chemical equilibrium is a state in which the rate of forward reaction is equal to the rate of backward reaction. It refers to the state of a system in which the concentration of the reactant and concentration of the product do not change with time. Now, how the enzyme lowers the activation energy barrier? What is the reason? So, in the enzyme catalyzed reaction, the catalytic functional group on an enzyme, which can be a specific amino acid side chain, a metal ion, or a coenzyme, it may form a transient covalent bond with a substrate and activate it for the reaction. Or a group may be transferred from substrate to enzyme. The covalent interactions between enzyme and the substrate lower the activation energy and thereby they increase the rate of reaction. Why? They provide an alternative lower energy reaction path. The interaction between substrate and the enzyme during the ES complex formation is mediated by hydrogen bonds or hydrophobic and ionic interactions. And full complement of such interactions between substrate and enzymes are formed only when the substrate reaches the transition state at the top of the energy barrier. Formation of each of these weak interactions in enzyme substrate complex are accompanied by the release of small amount of energy, and this energy is known as binding energy. This binding energy stabilizes the enzyme substrate complex and it is a major source of free energy used by enzyme to lower the activation energy of reaction. So if the reaction is uncatalyzed, the activation energy barrier is higher. And during the presence of enzyme, when the enzyme substrate complex is formed, binding energy is released which lowers the activation energy of the reaction and so the reaction becomes faster. Now we come to factors affecting enzyme activity. The factors that affect enzyme activity are temperature, pH, concentration of substrate, also the concentration of enzymes and the presence of activators or inhibitors. Enzyme activity increases on increasing the temperature. And optimum activity is reached at the enzyme's optimum temperature. At extreme high temperature, there is a sharp decrease in activity because the enzyme's active site change shape and the enzyme gets denatured. Enzyme activity is at maximum value at the optimum pH and each enzyme has its own optimum pH. For example, pepsin has an optimum pH of 2. It works best at an acidic pH. At the optimum pH, the rate of reaction is maximum. If we decrease or increase the pH value, the rate of reaction will decrease. For salivary amylase, the optimum pH value is 7. So it will show maximum activity at pH 7. If we decrease or increase the pH, the rate of reaction will decrease. Now we come to the effect of substrate concentration on enzyme catalyzed reaction. Initially, an increase in substrate concentration leads to an increase in the rate of enzyme catalyzed reaction. As the enzyme molecules become saturated with substrate, the increase in reaction rate levels off. And on further increasing the substrate concentration, there will be no increase in the rate of reaction. For enzyme catalyzed reaction, the graph between rate of reaction and substrate concentration is rectangular hyperbolic curve. Allosteric enzymes can be regulated by other molecules that are called modulators. And if the activator is present, rate of enzyme catalyzed reaction will increase, and in the presence of inhibitor, rate of reaction will decrease. Michaelis-Menten studied the effect of substrate concentration on the rate of reaction, and they observed that the rate of reaction increases with the increase in substrate concentration. Finally, when all the active sites of the enzyme molecule get saturated with the substrate, then the reaction levels off. There is no increase in the rate of reaction And the point when all the active sites of enzymes are saturated with the substrate is called Vmax or maximum rate. And this kind of saturation effect is exhibited by all the enzymes. When we plot a graph between rate of reaction and substrate concentration, a rectangular hyperbolic curve is obtained, and Michaelis and Menten derived a mathematical expression for this curve. At half maximum velocity, the substrate concentration in moles per liter is known as Michaelis-Menten constant or Km. Km tells us about the affinity of the substrate molecule for the enzyme. Lower Km means higher binding affinity or higher rate of reaction, and higher Km means lower binding affinity or lower rate of reaction. Michaelis-Menten equation can be represented as V0 is equal to Vmax S upon Km plus S, where V0 is the initial velocity in moles per time, S is the molar substrate concentration, Vmax is the maximum velocity, and Km is the substrate concentration at half maximum velocity. In this equation, V and substrate concentration are the variables, whereas Vmax and Km are the two constants. So with the help of this equation, we can calculate reaction rate of an enzyme at any given concentration of its substrate. The kinetic properties of allosteric enzymes or regulatory enzymes are different from non-regulatory enzymes. The non-regulatory enzymes give a rectangular hyperbolic curve when we plot reaction rate and substrate concentration. But the allosteric enzyme give a sigmoidal saturation curve when we plot reaction rate versus substrate concentration. And we do not use the designation Michaelis-Menten constant or Km because allosteric enzymes do not follow the hyperbolic Michaelis-Menten relationship. Instead of Km, we use the symbol S0.5 or K0.5 to denote the substrate concentration at half maximum velocity. When we plot a graph of rate of reaction versus substrate concentration for allosteric enzyme, we get a sigmoidal curve. When activator is present, the curve shifts towards the left side, and when inhibitor is present, the curve shifts towards the right side. And you can see in this graph that Km value is not constant. When the activator is present, half maximum velocity is reached at lower substrate concentration. And if the inhibitor is present, the Km value becomes higher. At higher substrate concentration, reaction will reach at the half maximum velocity. How the enzymes catalyze bisubstrate reaction? They may form a ternary complex, or the reaction may proceed without the formation of a ternary complex. For example, in the A diagram, the enzyme and both the substrates come together to form a ternary complex and then the products are released. In the B diagram, an enzyme substrate complex is formed, then a product leaves the complex and the altered enzyme forms a second complex with another substrate molecule, and then the second product leaves, regenerating the enzyme. Thank you so much. In the next lecture, I'll tell you about enzyme inhibition.